So we have here the graph of f of x equals sine of x. And as we've done before, we have underneath it a blank set of axes lined up only by the x coordinate to do a graphical analysis to draw the derivative. So what this requires is for us to draw tangent lines or be able to identify the slope of the tangent line at certain points on the graph of sine of x. Now, that's a difficult enough thing to do on a graph normally. As it turns out, there's really only a few points on a graph that we can automatically identify instantly what the slope of the tangent line would be. And as it turns out, those points are the places where the tangent line would be horizontal, which typically are going to occur at a place where the graph goes completely flat for a brief instant in time, and that kind of thing only happens at a maximum or a minimum. And we'll see that in a future lesson where we kind of formalize that relationship, but really what we've got here is simply that at any place where the sine function peaks or bottoms out, we're going to see a horizontal tangent line. The good news is, unlike non-periodic functions, we get an abundance of these from the sine function because it is periodic. Periodic functions do have that advantage to them. So, what we've got from this then is that at each of these points, at each of these x values, we find that the derivative function is equal to 0. The derivative function here is again equal to 0. And at each of these x coordinates where the original function has a horizontal tangent line, the derivative function is going to be equal to 0. Now, in between requires a little bit more careful analysis. We can't use specific values because, well, first of all, the graph may not be completely 100% accurate because it is hand-drawn. But second, the scale is very difficult to work with. The scale on the x-axis is, of course, in terms of pi because the trigonometric functions are done in terms of radians. The inputs are angles in terms of radian measurement. So that makes for some really difficult slopes, even if we had concrete points to work with. That being said, the general trend of the slopes can still be ascertained pretty easily. So, for example, as we move from this maximum point down towards this minimum point, any tangent line we draw will be negatively sloped. And the further we go, the steeper that negative slope will be. At least until we get partway through. Once we reach pi, we have our steepest negative slope, and then we start to flatten out again because our slopes have to come back towards 0. So what we see is that the derivative is going to track through negative slopes, getting larger and larger in magnitude until we hit negative pi, and then coming back, still negative, but coming back towards a slope of 0. Actually, when you look at it, we get the exact same relationship going on here, where we have negative slopes that are increasingly steep until we hit pi, at which point they start to flatten out again. And then we see the same thing on this section. Again, this is the very nature of a periodic function, is that it repeats its behavior on intervals of fixed width. So every time we go from a point where the sine function has its maximum down towards where it has its minimum, we see all negative slopes that are small in magnitude at first, getting to be the steepest with the largest negative slope in the middle, and then coming back up towards 0, and again over here. In between, we see exactly the same thing. The shape of the sine function through a negatively sloped portion is actually the same as the shape through the positively sloped portion, just everything's positive. We start out with a slight positive slope, and then a steeper positive slope, before going flatter again and coming back to 0. So we see the same activity, but this time with positive values of the derivative. And we'll see that again in the next section. And so on and so forth. And what we get then is, not surprisingly perhaps, another periodic function. That should, I hope, make a degree of sense. The sine function is periodic. Its behavior repeats. Its pattern of output values repeats, which means the change in the output values, the rate of change of the function, has to also repeat. But now take a look at the function that we've graphed. Now, admittedly, we don't actually know the scale of the y-axis just from this. But that being said, the PowerPoint slideshow does include the algebraic derivation of this, which does show us that not only is this a cosine function, but it is the cosine function, meaning its amplitude and whatnot are those of the basic cosine function. So from that, we know that the scale on the y-axis here is the same as the scale on the y-axis for the original function. And we have that the derivative of sine of x is cosine of x. Now, cosine of x is another basic function, so we would want its derivative as well, but that's actually very easy to find. We can follow the same basic procedure, but this time we'll do it down to the third set of axes below it. So again, we'd start with the idea that wherever this wave has its maximum or minimum and is therefore completely flat for one brief instant in time, that's where its tangent line would be horizontal. Again, that is the only reliable point that we can get graphically, because regardless of the scale of the axes, we know exactly what the slope is, because the slope of a horizontal line is always 0. So at the x value of negative 2 pi, the derivative of the cosine function is 0. At negative pi, the derivative of the cosine function is 0. And at x equals 0, the derivative is 0. At x equals pi, at x equals 2 pi, at x equals 3 pi, and at x equals 4 pi. Every one of these, of course, corresponding to where the cosine function is completely horizontal for one brief instant in time. In between then, well, the cosine function and the sine function are basically the same function, just slightly shifted from each other. So the behavior of the cosine function as you go from a maximum down towards a minimum is the same as what happened when the sine function went from its maximum to a minimum. So when the sine function went from max to min, its derivative bottomed out. So when cosine goes from maximum to minimum between negative 2 pi and negative pi, its derivative will go through its negative values bottoming out in the middle and coming back towards 0. As the cosine curve goes through its positive rate of change, just like sine did it from negative pi over 2 to positive pi over 2. Cosine did it from negative pi to 0. So from negative pi to 0, we again have that same kind of behavior. This behavior will continue as the cosine function repeats its pattern of output values and therefore its rate of change of output values. And what we get here is, well, not the original sine function. Actually, we get the vertical reflection of it. So here we can say that the derivative of cosine of x is actually equal to the vertical reflection of sine of x. So again, graphical analysis can be very handy. It's not always easy to do with specific values, but sometimes it's enough to get a general feel for what's going on. Now, again, we have the vertical axis here where we don't know exactly the scale, but I think it's probably safe to assume that if the scale did not change going from sine of x to cosine of x, then it probably won't change going from cosine of x to its derivative, negative sine of x. Actually, when you think about it, we know this scale, it peaks at 1 and it bottoms out at negative 1. We know that from the algebraic approach that we saw in the PowerPoint slideshow. So what that actually tells us is in the middle of each upward or downward swing, in the dead center where it is steepest positive or steepest negative rate of change, the rate of change is actually positive 1. The slope of the tangent line right there is actually positive 1. And the slope of the tangent right here at pi is actually negative 1. Well, if cosine is the same waveform as sine of x, it just starts in a slightly different place, then when cosine of x is at its steepest, its slope should also be either negative 1 or positive 1. And from that, we can surmise that the scale on the y-axis is again the same.